All right, we have this example coming from this population or predator-prey population model. This matrix, same matrix we've been using. Columns are 4, 1, and minus 2, 1. We found the eigenvectors. We call them V and W. Let's say 1, 1, and 2, 1. Actually, we might have used 10, 10, and 20, 10, but it doesn't matter. We can scale eigenvectors, so I'm just going to use 1, 1, and 2, 1. And they were eigenvectors with like AV equals 2V, so that's an eigenvector with eigenvalue 2, and AW is 3W. So W is an eigenvector with eigenvalue 3. And we used the eigenvectors to compute basically what happened when we wanted to multiply repeatedly by A, right? So A to the n times P naught, some initial population vector. P naught is some initial population vector. Right, and we sort of said, okay, well, because A acts nicely on V and W, we could write P naught in terms of V and W, right? Write P naught in terms of V and W as a linear combination of V and W. And that will give us, then we can, we did that. We actually had a P naught that was V plus W, and then we use the fact that multiplying by A just doubles V and just triples W to be able to sort of like figure out, if we did that repeatedly, how that would affect P naught. So so that was the predator-prey video. But I want to talk about something else. So like, what if we wanted to compute just A to the n directly? It seems like that should be something we should be able to do. Right? As like an actual matrix. There we started with an initial vector and then computed what happened when we multiplied by A repeatedly. But what if we actually wanted, A to the n is some 2 by 2 matrix. And what if we actually wanted to compute that? Well, here's the idea, right? And it's going to be I'm going to sort of generalize what we did in that predator-prey video right here. So let's generalize that. And the idea was that actually V and W, this is a basis, right, for R2, for the plane. These point in different directions, so this is a basis. It's actually called an eigenbasis. So if you have a basis made up of eigenvectors, it's actually called an eigenbasis. And that means we can write any vector in the plane as a linear combination of V and W, right? So given any x, so I'll just write that as x1, x2, we can rewrite it as C1, V1, sorry, not V1, but V, C1V plus C2W for some choice of C1 and C2, right? Just as an example, if I took something like 7, 10, I claim that that's the same thing as 13V plus negative 3W. Because if you work it out, you can check. If you actually write this out, you can check that this works. And so, you know, we can do this for any vector. I could start with any two, like 7 and 10 were arbitrarily chosen, and I can always write it as a linear combination of v and w. So in general, we have this equation right here. And before I even get an A, I just want to do something kind of goofy. I want to rewrite this. We've actually started to notice, hopefully more and more, that whenever we have a linear combination of vectors, we can actually rewrite that as a matrix times a vector. Right, this is the matrix whose columns are v and w. Whose columns are v and w. Right, in fact, it's really just the matrix 1, 1, 2, 1, I think, because that's v. This is v right here. And this is w. Okay. And I want to think a little bit about, well, actually, okay, let me do a couple things here. I want to give this matrix a name. So let's actually call this matrix B. So we have B, so B equals the matrix whose columns are 1, 1, and 2, 1. Okay, and B sort of for basis, you know, because this is an eigenbasis, because it's a basis, sometimes this is, and it's going to be called a change of basis matrix. In fact, if you think about it, if we call this vector C, then we have something like x equals bc. And if you think back to the change, there's actually a change of basis video that 3 Blue 1 Brown did. This is sort of in standard coordinates, right? Like we had something like 7, 10. And that's just, we think of that as 7i plus 10j. But C is in the VW coordinates. And somehow B is a change of basis matrix. It actually is how we change from the VW coordinates to the standard coordinates. So it's called a change of basis matrix. That's its name. And this is going to end up being very useful. I said the whole goal was to compute powers of a matrix and powers of A, that original matrix we had, but I claim this is going to be useful. Because let's think about what happens now if we do A times X, right? Let's just actually go through that. So A times X. Well, if we rewrite, and I'll come back to this notational stuff in a minute, but I'm just going to do it sort of naively first. So if we rewrite this as C1V plus C2W, well, we can use linearity, and this is kind of a generalization of what we did in the predator-prey video, where I sort of say, okay, well, I want to just think about actually putting the A inside, sort of distributing it over the multiplication and also over this, distributing the multiplication over addition and distributing it through the scalar multiplication, and we get C1 times AB plus C2 times AW, right? That's C1 times 2V plus C2 times 3W. And I want to do something similar to what I did up here. I want to do something similar as like here as we factor. And so I could actually rewrite this then as the matrix whose columns are 2V and 3W times C1 and C2. Okay, that's sort of interesting. It's definitely not B. B is the matrix whose columns are V and W. This matrix has columns 2V and 3W, but I have a claim. I claim that this is the same thing as the matrix whose columns are V and W multiplied on the right by this diagonal matrix, where the diagonal is 2, 0, 0, 3. The elements are 2 and 3, and everything off the diagonal is 0. We can just check that in general, right? Like, we just took like an ABCD matrix and multiply by 2, 0, 0, 3. You can actually check this, that you get 2A. You actually get 3B, 2C, and 3D, right? So actually, you've doubled the first column and you've tripled the second column. And so that actually does, that does work. So let me go back to this argument again now. Okay, so now we have AX is, well, it's the matrix VW, the matrix whose columns are V and W, times 2, 0, 0, 3 times C1, C2. Okay, couple things. This is kind of just an algebra argument. I'll give some sort of like geometric argument that's very similar to what's given in the 3 Blue 1 Brown video in a minute, but I just want to give this sort of algebraic argument first. That's B. I'm going to call this D for diagonal matrix. If I make it look like a D. What about C1, C2? What about that vector? Because it's not really, we still need to know what C1 and C2 are. Like, if you think about it, we're just trying to multiply A by a general vector x1, x2, right? But if you go up here and think about this equation we had, right? I can actually rewrite this. I can also write down here that C is B inverse X. Okay, and so that means that C1, C2, we can think of that as B inverse times x1, x2. And if we do that, then we actually get, we put that all together. It's kind of a lot going on here, but when we put it all together, we get this equation. We get AX equals, we have the matrix B right here, right? Times D right here, and then times B inverse. And this is really B inverse X, right? So B inverse X. So we have BD inverse times X. And that's kind of cool because, like, it's almost like we've taken A. It sort of X doesn't really matter. It's just this actually implies that A is BDB inverse. And this is a nice construction. It's kind of an interesting thing that's going on here, that D is diagonal with the eigenvalues on the diagonal, right? The 2 and the 3. And this is sort of a way, we've taken A and we sort of factored it in an interesting way, actually. Let me write it even more explicitly. So it turns out, so B was the matrix, we said whose columns are 1, 1, 2, 1. You can compute B inverse. I wrote it down for myself, and I got -1, 1, 2, -1. I think that's the matrix B inverse. You can check. Hopefully that works out. And then D is the matrix, like we said, whose it's diagonal matrix where the eigenvalues are on the diagonal. And so you can check that our original matrix. You could actually, I mean, you really should write this out just to check. You should do it once. It's supposed to be BDB inverse, right? So that's BE times D I sort of gave an argument just using algebra, matrix algebra, why matrix vector algebra, why this should work, but it's a good idea for you to write this out and check that actually, if you multiply those three matrices on the right out, you actually get the matrix on the left. Okay, so this is a cool thing. This is called diagonalization, because we've sort of written A in terms of a diagonal matrix. And it's got this nice sort of structural thing where you're multiplying the B on one side and the B inverse on the other side. That's a name for that in mathematics. That's multiplying something in its inverse on either side is actually called conjugation. We've actually done something already like this when we computed matrices for projections and reflections. We actually did sort of rotate, project, and rotate back. And that's sort of like doing a B inverse and a B on either side of another thing. So anyways, maybe I'll make that connection more explicit in another video. But this is called diagonalization, and it's interesting. So, you know, also I should mention, I mean, D is eigenvalues on the diagonal, and actually B is the matrix whose columns are the eigenvectors. So it's not even just just gonna write that over here. It's not even that just the eigenvalues show up, but actually the eigenvectors show up. Right, and the first column was V, which was the eigenvector that went with eigenvalue 2, which was the first diagonal entry. And right, like this went with this number right here, and this column, the second column, goes with that number right there. And so it actually is kind of this thing where we've sort of taken our matrix and rewritten it fully in terms of just the eigenvectors and eigenvalues, which is really cool. And you get this sort of diagonal matrix in the middle. And so this is kind of an exciting thing to do. Well, maybe it's not so exciting, but it's kind of interesting that we sort of factored a, maybe I'll write that out and put that in sort of quotes. We factored a using the eigen stuff. Okay. Now I want to see how this is going to pay off. So remember, we wanted to compute, so go back. We want to compute a to the n. You know, just power. We're going to compute powers of a. Well, let's think about a squared for a second. And also we know a is BD, B inverse. Let's think about a squared. Well, that's BD, inverse times BD, inverse. Do you see something interesting there? You should be excited right now. These cancel, and we can drop the parentheses, and the B inverse and B will cancel each other out. And so this actually equals BD squared B inverse. That's interesting. If we do it again, a cubed, well, that's a squared times a. And we know a squared is BD squared B inverse, and a is BD B inverse. And it happens again. So that is BD cubed B inverse. And you can see that this is going to work in general, right? A to the n is sort of BD B inverse times BD B inverse dot, dot, dot. You know, n times, we're multiplying this together. And all of these middle B inverse B's cancel. Right? There's some stuff in the dot, dot, dot that end up canceling. And this ends up equaling B d to the n B inverse. And this is actually like astonishingly easy to compute. write like, in fact, we can just do this in general here. Like, if you think about if D is 2003, then what's D to the n? Well, you can check for yourself. It's not that hard to see. That's actually 2 to the n, 0, 0, 3 to the n. You're just multiplying this sort of the numbers that are in the same place by each other, and that's all that ends up getting multiplied by. So that means that if we wanted to take the matrix 4 minus 2, 1, 1 and raise it to the nth power, we can actually just multiply. We can actually just do this diagonalization procedure and write down b d to the n, and then b inverse, which let me just double check what b inverse was, minus 1, 1, 2, minus 1, yeah. And multiply this out, and you get a formula, a direct formula. It's kind of, you know, it's not the nicest formula maybe, but it's a direct formula for the power. So let's actually do that. So we get 2 to the n, I think 2 times, I'm just going to multiply the first two matrices first. 2 to the n, 3 to the n. We take that, and then we multiply by minus 1, 2, 1, minus 1. And we get, you know, it starts to look a little bit ugly, but whatever. Minus 2 to the n plus 2 times 3 to the n. Actually, yeah, okay, fine, I'll just write it the way minus 2 to the n plus 3 to the n, 2 times 2 to the n, which I guess is 2 to the n plus 1, minus 2 times 3 to the n, and 2 to the n plus 1 minus 3 to the n. And that actually works. This actually tells us, we actually have a formula for the nth power. So a to the n, if a is the matrix 4, 1, minus 2, 1, then a to the n is, we actually found a formula just using the eigenvectors, eigenvalues. And so this is, we sort of saw already how that was useful in iterating a discrete dynamical system, but how having the eigenvectors, eigenvalues, but this actually even works just on the general matrix level. And we can actually compute powers of the matrix. But it all came down to this formula right here, that we were able to somehow rewrite the matrix in terms of a diagonal matrix, and that was easier to compute its powers. And so that's what's called diagonalization. And it sort of falls out naturally from the algebra. Maybe one last thing I'll say is that if I actually just want to say this again, that I'll write this as many times as I can, A equals B times D times B inverse. Well, B, we said all the way back up here that B sort of translates, I said it was a change of basis matrix, right? It sort of translates from the VW coordinates to the standard coordinates. So let me go down and write that. So B is sort of a way to translate from VW coordinates to the standard IJ coordinates, just where we normally write. IJ coordinates. B inverse then goes backwards. It goes from standard coordinates and converts to the VW coordinates. In fact, you can see that in this example all the way back here. Where's that example I did? Yeah, in this example right here, I actually found this by, I started with 7, 10, and I sort of converted. I started with standard coordinates and converted to the 13 and the minus 3 were the VW coordinates. And I claim I can get that just by multiplying by B inverse also, right? So for example, if we take B inverse, which again was this matrix and we multiply by 13, -3, because that's what, I'm sorry, no, times 7, 10. That's actually, it's really easy to get this backwards, so just be careful. Like the 7, 10 was the standard coordinates, so this is B inverse, and this was sort of X in standard coordinates, right? If we actually multiply this out, you get -7 plus 20, which is 13, and you get 7 minus 10, which is -3, which was in the VW coordinates. So you can actually see how the conversion happens. Okay. Well, okay, so if we think now back up here to what this does, is we remember that when we multiply matrices, we're sort of reading them right to left. I don't think about them as transformations. So in other words, to compute what A does, because A is some sort of transformation of the plane, right? We've always seen these, and the 3 blue, 1 brown videos do a really good job of showing this. So if we take this sort of transformation viewpoint, so we go right to left. And so if we want A as a transformation, we can sort of think of first, so to see how A works as a transformation, first, switch from standard coordinates to VW coordinates. To the eigenbasis coordinates. And then in the VW coordinates, the transformation is really easy because it just doubles in the direction of V and triples in the direction of W. So in VW coordinates, the transformation really is this diagonal matrix. Transformation is that, right? Because all you're doing is you're just thinking everything in terms of V and W coordinates. You're just doubling in the V direction and tripling in the W direction. So that's actually the transformation is diagonal in that. Again, the videos from 3 Blue 1 Brown have much nicer pictures of this. But then, so you actually, so this is the switch. The first step is the switch basis step. The second step is actually perform the transformation and then switch back to standard coordinates. And so that's really, if you think about what's happening, is this first step is given by multiplying by B inverse. Then, V inverse times something. Then the second step is given by D times the previous step. And then the last step is given by B times the previous step. And so in other words, what is A really? Well, what you do is you just write right to left, you write the B inverse, which means you switch from standard coordinates to VW coordinates, multiply by D, which is the transformation in the VW coordinates, and then you multiply by B, which switches back. And so it's the same. It gives you sort of a geometric reason why this formula works and where diagonalization comes from. Okay, I will stop there.